You ever notice that weird contradiction with AI today? I mean, these models can write poetry, they can debug complex code, they can even explain quantum physics, but then you stick one in a robot and suddenly it's surprisingly clumsy. Well, today, we're going to dive into a pretty groundbreaking solution that wants to fix exactly that. It's a new framework called TIGeR, and believe me, it completely flips the script on how AI interacts with the physical world. And this question, this right here, it really gets to the absolute heart of the problem. We've got these AIs with mind-blowing language and reasoning skills, but they're missing the one thing a robot absolutely needs to function in the real world: metric precision. It's this fundamental gap between, understanding a concept and actually executing it with real-world accuracy. So what's the missing piece? And there it is. That's the whole ballgame. For years, we've trained AI to recognize patterns and make these incredibly educated guesses. We've basically taught them to be brilliant estimators. But for a robot to work reliably, it can't just estimate. It has to compute.
So this brings us to what the researchers are basically calling the clumsy robot problem. And it's not about a lack of smarts, not at all. It's about this fundamental disconnect between an AI seeing the world and being able to precisely measure it.
Okay, check this out, because this slide makes the distinction super clear. Current AIs, they are masters of what's called qualitative reasoning. They get relationships like left of or behind, no problem. But robotics, that demands quantitative reasoning, the ability to say exactly how far, down to the centimeter. That's the huge difference between a helpful description and a command a robot can actually follow. So why is this gap so huge? Let's get into the nitty-gritty of why these incredibly powerful models just fall flat when it comes to precision. This right here is the root cause. When a standard vision language model looks at a room, it doesn't see a 3D space with coordinates and angles. It sees pixels and patterns. It's been trained to make a statistical guess based on millions of other images it's seen. It's not doing the math. It's just recognizing a familiar picture. It's treating geometry like a pattern, not a calculation. All right. So that brings us to the solution. It's a completely new way of thinking about the problem, and it's called TIGeR. And here's the key. It doesn't try to make the AI a better guesser. Nope, it gives it a whole new skill. And I love this quote because it just makes the whole concept click, right? It's so intuitive. We don't need the AI to do all this complicated math in its head. We just need to teach it to recognize when a math problem needs solving, and then give it the right tools for the job. So to get official for a second, TIGeR stands for Tool-Integrated Geometric Reasoning, and its whole goal is to fundamentally transform these AIs from being simple perceptual estimators into powerful geometric computers. And it does it all by letting them use external, specialized tools. Okay, so how does this actually play out? Well, TIGeR uses this really clear four-step process. First, the AI perceives the request, something like place this cup 5 centimeters from the edge. Then, and this is the magic part, instead of guessing, it actually generates the computer code needed for that specific calculation. Step 3, an external tool runs that code using real sensor data. And finally, the AI gets the precise numerical answer back and uses that to complete the task. Simple, but brilliant. But of course, you can't just hand an AI a calculator and expect it to know what to do. You've got to teach it. And to do that, the researchers basically built it a massive, custom-made textbook. And the scale here is just wow. They created a dataset with 300,000 high-quality training examples. Think about that. Each one is designed to teach the AI not just what the right answer is, but the exact steps and the exact tools it needs to use to get there on its own. And this dataset, it's incredibly rich. It's not just questions and answers. It includes the entire thought process, the specific tools to call, the intermediate math, the reasoning behind it. It covers everything from simple stuff like point transformations to really complex multi-view scenarios. It's a full-blown education in geometric problem solving. So the teaching itself happens in 2 stages. First, you've got supervised fine-tuning. That's like the AI studying that massive textbook, just learning the basic patterns from those 300,000 examples. But then comes reinforcement fine-tuning, which is more like doing homework with a tutor who gives you feedback. This is where the AI really perfects its skills and learns to handle totally new problems. Okay, so the theory is solid. The training is intense. But does it actually work? Let's get to the good stuff and look at how TIGeR performs when it's put to the test.
both in benchmarks and with actual physical robots. Here is a perfect example from the research. A simple-sounding question, but one that requires some real geometric chops to answer correctly. So how would a standard AI handle this versus our new TIGeR model?
Man, the difference is just night and day. A top-tier model like Gemini does exactly what we talked about. It makes a qualitative guess. It eyeballs the floor tiles and estimates, 12 to 18 inches. TIGeR, on the other hand, does what it was trained to do. It calls up the right tools, gets the precise 3D data, writes the code to calculate the distance, and comes back with the exact answer, 2.52 meters. It is guesswork versus calculation, right there on the screen. And this ability translates into huge performance gains in robotics. In a really complex robot simulation, other models were averaging about a 40% success rate. TIGeR more than doubled that, hitting nearly 84% success. I mean, that is just a massive leap in reliability.
But the results get even more wild with a physical robot. For a super precise task, like placing an object exactly 10 centimeters away, TIGeR nailed it 55% of the time. The next best model, only 10%. And look at this. For tricky tasks involving objects being hidden or in complex spots like to the back or above, other models just failed, a 0% success rate. TIGeR, meanwhile, was handling them with 60 to 70% success. It's not even a competition. So, what's the big takeaway from all this? What does it all mean? Well, TIGeR is way more than just a clever trick. It's a fundamental shift in how we should be thinking about AI for the physical world. This quote from the research paper just nails it. It perfectly sums up the leap we're seeing. We are moving beyond AIs that can only describe the world to AIs that can accurately compute within it. And that right there is the key to unlocking the next generation of robotics. And that leaves us with a really fascinating thought to end on. For the very first time, we're giving our most advanced reasoning engines the tools they need to interact with our world with mathematical precision. This just blows the doors open for possibilities we're only just starting to dream of. Things like autonomous construction, high-precision manufacturing, you name it. The question isn't if AI can do it anymore. The real question is, what are we going to ask it to do next?